So this is another practice one where we're just going to practice using our intervals and radius of convergence. So this time we don't have to generate the Taylor series. We've been given the Taylor series for this function, 1 over x, and it's centered at 2, so we can see that that's where the center shows up. So what we're going to do then is we're going to just start with our radius of convergence. So we're going to do our ratio test. So limit as n goes to infinity. -1 to the n plus 1, x minus 2 to the n plus 1, okay, all over 2 to the 2n plus 3. Okay, so we're going to plug in n equals 2. Oh, sorry, that's not going to be correct. So we're going to do, that's just going to be n plus 2, because we're going to add n plus 1 in there, so plus 1 is plus 2. Okay, so then we can just put in the rest, the original on the bottom, and so that's 2 to the n plus 1, and then we're going to do the ratio test, see where this is equal to or less than 1. Okay, so limit as n approaches infinity. This is going to be just -1. We're going to end up with x minus 2 to the power 1, and then here we're just going to end up with well, I'm going to write this out, so it's going to be 2 to the power n plus 1 on top, and 2 to the power n plus 2 on bottom. Okay, so we're going to simplify that exponential expression before I do the limit. So limit as n goes to infinity, it's going to be negative of x minus 2, and this portion here is going to simplify to 1 over 2. We're going to just have an extra factor of 2 in the denominator. Okay, so then there's no more n's left now, so that's kind of nice. If I let the n go to infinity, that's pretty easy. I'm going to end up with negative x minus 2, and then I'm just going to multiply both sides by the 2, and so I end up with 2 on this side. So we can see that the center is going to be at 2. The radius is now going to be 2. So when I do my interval looks like this. It's going to be from 0 to 4. Okay. And this is a quick way to do it if you know where the center is and you can recognize the radius. So once I've done that, I still need to test my endpoints. So I'm going to test x equals 0 as my endpoint. So when I plug that into my series looks like this. N equals 0 to infinity, -1 alternating, and then we end up with -2 to the power n. So when we have this, we're going to have this situation where if n is odd, okay, we're going to end up with negative times negative. If n is even, that's going to be positive and positive. We're always going to end up with a positive term. Okay, so we end up with that over 2 to the power n plus 1. Okay, now that becomes irrelevant because even though the numerator is positive, this is going to converge absolutely because it is a geometric series. Okay, it's got a geometric series exponential function in the denominator. So I know this converges, so I include that endpoint. Okay, so this is convergent. Okay, so that endpoint, I'm going to do in red. Okay, when x is equal to 0, okay, it's convergent, so we're going to include the 0 endpoint here. Okay, then we can test our other endpoint, x equals 4. Now, when we look at this, we can see that that's a geometric series in the denominator, so we should kind of have a sense that it's probably going to converge. Okay, now even if we don't have that sense, we can always just test. So I'm going to go -1 to the power n. This is going to end up being power 2 to the power n, so this now becomes alternating. But again, it's alternating geometric series. Well, it doesn't matter if geometric series alternates, it still converges. Okay, regardless, remember that this converges absolutely. Okay, so then because that endpoint converges, our x equals 4, is convergent. So again, we're going to include that as our endpoint. Okay, so there becomes that is our interval of convergence is going to be from 0 to 4, and it's a closed interval of convergence. It includes both endpoints.